This is Unit 8, Video 13. In this video we will talk about pH, a very important scale referring to acids and bases. Now, the picture that you're looking at is actually another indicator which we didn't mention, called universal indicator. And the neat thing about universal indicator, which is present in all chem laboratories, is that it follows the colors of the rainbow, from red, orange, yellow, all the way down to purple. And at a pH of 1, which is acidic, as we'll see, you begin with red, and as you increase the pH, as you make it less acidic, more basic, you get to circle all the way around to the other color, purple. Now, the way they do this is there are actually a bunch of indicators put together. So there's maybe 4 or 5 different pigments, indicator pigments, that are used to create all these colors, but this has been traditionally done for a while, so enjoy universal indicator. We'll do a few examples in class with them. But pH. pH is a scale of acid-base strength, and really it goes from 0 to 14, but you can actually dip down below 0 and go above 14, but standard is 0 to 14. And it is a logarithmic scale. Now, logarithmic means the change on the actual scale corresponds to a very big change in actual measurement. So this is kind of the same scale that's used for earthquakes. You may have heard of the Richter scale, which an earthquake that's a magnitude 7.2 versus one that's 8.2 is not just a little stronger, it's quite a bit stronger, 10 times stronger or so. So this is a similar scale, and so we'll see, going from a pH of 0 to a pH of 1, that's a 10-fold increase in magnitude, you can say. Now, if you are 7 is considered neutral. So here you have a little graphic showing some interesting solutions that have these pH values. So pure water is actually a pH of 7 by definition. And if you're below 7, less than 7 will be acidic. So for example, tomatoes are acidic. And lemon juice, we talked about stomach juice, which is actually hydrochloric acid. And pure hydrochloric acid in the laboratory will have a pH value of 0. But if you go the other way, basic, greater than 7 will be basic. So as we increase, baking soda is a famous base, weak base. And then we have ammonia, which is the cleaner used. And then out here we have the strong base, sodium hydroxide, which is given the pH value of 14. So at the lowest value you have hydrochloric acid, the famous standard acid in the chem laboratory. At the high scale you have sodium hydroxide, the famous base of the chem laboratory. And we'll talk about how to determine these values and what these values mean. Now, you'll notice that here you can actually see the logarithmic scale of it. You'd see that between 10 to the negative 9, 10 to the negative 8, that's 10 times greater, where the pH change is just 1, from 9 to 8. You actually have a 10-fold increase or a 10-fold decrease. So that's what we meant by a logarithmic scale. So pH actually measures, you can think of it as the power of hydrogen. And it should be hydrogen ion, because it's hydrogen, the ionic hydrogen we're measuring. And it measures the molarity of the ion in solution. So we're actually going to be talking about molarity. We mentioned how important molarity is as the concentration unit. So as the concentration of hydrogen ion increases, the pH will decrease, because acidic substances which produce hydrogen ion have low pHs. Mathematically, here's what the equation looks like. pH equals negative log of H plus. So this is actually an operator, a mathematical operator on every calculator that's scientific should have a little log button. Now you'll have to put a little negative in front of it, because as you'll see that logs of small numbers will give you negative values, so you'll have to cancel that out with this negative in front and for it to make sense. So we'll do an example and we'll point this out. So what's the pH if the hydrogen ion concentration is 8.20 times 10 to the negative 50? So all you have to do is plug that into the calculator. Really what you're doing is, so if I just write this out in standard notation, like so, you're just really plugging that number into your calculator. Now if you do this, there should be a little log button, so you get 4.09 for the answer. that's actually the answer. Now, the other interesting thing about this is that pH has no units. This is another one of those values that has no units. So, and partially why it has no units is because here's what the log operator does. Let me go a little bit into, from math, what this is. The log button actually undoes the power. It pulls out what the power is. So, for example, if you have a number, if the number is 1 million, and that is a million, and if you log this number 1 million, if you decide to ask the calculator what's the log of 1 million, what the calculator essentially is saying is 10 to the what power is a million. So it's actually finding the power of that number, and that's why we call pH the power of hydrogen. It's really the power, in a mathematical sense, of that number. So in this case, the power is 6, and because this number here, a million, can be written as 10 to the 6th. So that's how we get a log of 6. Log, this is a log base 10. Logs, if you know about them, have different bases, but we're using a base 10 because we're using the scientific notation that uses base 10, essentially. So if you were to do this number, essentially what you're asking as you're logging this number is, well, 10 to the what power equals this number. Now, this is pretty close to this number right here. This is actually pretty close. If you round this up, what you'll get is roughly this number, 0.0001. If you write that in scientific notation, that's 1 times 10 to the negative 4th. And what happens is the negative 4th is the power. And notice that's why it matches 4. Now, you get rid of this negative, that's why this negative in front is here, and to match the 4. So all this doesn't make any sense. As long as you can find the negative log button, you'll be safe in the calculator, but it's a good idea to understand how this works. And it is called the power of hydrogen for this reason. It pulls out the power that corresponds to the concentration. Alright, let's quickly do another one that's very similar. Instead, in this case, what we're doing is we are asking to solve for molarity first. So it says, what's the pH of a 0.20 moles of nitric acid in 4 liters of solution? Now, to get the pH, the negative log is determined of the concentration of H+. Remember, these brackets actually mean molarity. So we'll first have to find the molarity of our solution. So molarity is moles over liters. In this case, we have 0.20 moles over 4 liters, which gets us 0.05 for the molarity. Now, you'll have to negative log this, so just go ahead and pull out your calculator and go ahead negative log this number. Now, you should get yourself a value of exactly, let's see what we get, 1.3 with 2 sig figs. So this is actually 1.3 for the pH. Again, no units. So just make sure you have the molarity in there. Okay, what if we have a basic solution, not an acidic solution? How do we get the pH? So we determine something called POH, which is, notice, very similar. POH stands then for the power of hydroxide ion. And mathematically, it's defined the same way. POH equals negative log of OH minus. So realize as the amount of hydroxide increases in solution, which means we're becoming more basic, the pH actually goes up because basic solutions have high pHs. So the equation is really much the same. Now, what you do then, how do you get from POH to pH? That's the next question. And we do that through this simple equation. pH plus POH equals 14. So if you have your POH, to get the pH, you simply subtract POH from 14. 14 minus POH. So it's we'll do a few examples here in a minute. Now, this equation works because the hydrogen ion and the hydroxide ion concentration in pure water are actually equal. And there's a fun equation that if you take AP chemistry or college level chemistry, that'll be very important with acids and bases. And this is the equation. Now, the way this equation relates is this equation is actually the same thing as this. If you negative log all the way across and use properties of logs from math, you'll actually end up with this equation here. So for our purposes, pH plus POH equals 14. You can also use this equation if you'd like to solve. In fact, in this equation, it says if you know your hydroxide ion concentration, you can actually determine your hydrogen ion concentration through this number here. So why don't we do an example or two. What's the pH if hydroxide ion is 0.039 molar? So what we'll first find is the pOH. Let's do it in blue as corresponds to bases. So the pOHs, negative log of 0.039. Let's go ahead and find what that is. So plug this number into your calculator, 0.039, 1.41 in this case. So now to get the pH, you simply subtract from 14, 1.41. So 12.59, 3 sig figs. Actually here, we're going to end up with 4 sig figs because we're subtracting. This is technically 14.00 exactly. This is an exact number. So you get 2 sig figs, actually. Good. Again, no units for pH. So pretty simple. We got one more. The reason why we have this one is also to realize that if you want to solve for pH, you must be in molarity. So this is a base, KOH. Notice this is basic, and we have 1.2 grams of KOH. So we'll have to do a little calculation for the molar mass. So I have to convert 1.2 grams of KOH into moles. So grams of KOH here in a mole. And the KOH, hydroxide should be 1701, K should be 3910. So we should have 5611. So 1.2 over 5611 should give us 0.021. Let's do 39 just in case. This would be moles. Now to get the molarity, we want to divide that by liters. In this case we have 16.1 liters. We should get ourselves 0.01328 for the molarity, and this is the number we negative log. So if we do pOH in this case is negative log 0.001328, we should get ourselves go ahead and plug this in. Let's see what we got. Takes a little bit to plug in the negative logs. We should get ourselves 2.88. We have 3 sig figs. Let's see, we have 2 sig figs, so really 2.9 in this case. 2.9 for the pOH. And to get the pH again, pH is 14 minus that, which should be 11.1. Good. So 11.1 is the pOH. Now notice that corresponds to it being a basic solution. For a base, we want a high pH, and that's a good thing to check at the end to make sure you have a high pH if you indeed have a base. Alright, let's finish up by talking about reversing this. What if we're given the pH or pOH and asked for the concentration of the hydrogen hydroxide? So what you would do is you would undo the negative log equation, pH equals negative log of H plus. If you undo this mathematically, you get yourself H plus equals 10 to the negative pH. So it's just a matter of rearranging. If you know how to rearrange logs, then you get up to this. And same thing for pOH. So hydroxide ion concentration is 10 to the negative pOH. So pretty simple. And you can be asked about this. So what's the H plus in a solution with a pOH of 12.4? So what we could do first, we can get the pH. We know pH again is 14 minus 12.4, which gets us 1.6. And then the H plus is simply 10 to the negative 1.6. Now this should be a small number because we're raising it to a negative power, and hopefully we get some number that is worthy of consideration. It looks like my calculator currently does not have this function, so we'll let you figure that one out. All right. I mean, technically you can call this 10 to the negative 1.6. You know, 0.00 something will be the answer. Now, this will actually have a unit. This will be molarity, because what we're solving for is H+, the concentration of H+, and this will be that molarity. I mean, technically you can really say that this is the answer, 10 to the negative 1.6 molarity. But go ahead and compute it. That way we have a nice number that we're used to, you know, 0.00 something, and we'll end up with that. All right. So to wrap up, we have this called pH map, and essentially it allows you to see how all these pH, POH are connected. So pH is what we usually go for. This is what we want to end up at. And if we're given the H plus here, we simply use this equation, negative log of H plus. So you kind of have to read it sideways. If you want to go back to H plus, then that's 10 to the negative pH. Now, if you're given POH, you can simply subtract from 14 via this equation and get to pH. If you're given hydroxide ion concentration, if you're a base, so you have a bunch of a base, you can first negative log that through this equation, and then subtract from 14 and get to good old pH. You can also go this route. What's interesting is you can actually do from OH minus, you can use this equation if you'd like. This is the equation we showed you that relates to the top equation. You can go that route as well. Get the H plus and then get the pH. So we'll provide these equations for you as you need them on the test, and then we'll do this video in the next concept.